I welcome you all for the 13th lecture by NCTS. Today we will learn about die casting defect analysis from Mr. Rajesh Agarwal. Mr. Agarwal has over 30 years of experience in the field of product and tool design for aluminum die casting components in automotive and non-automotive sector. A recipient of Best Casting Award in Alucast and NADCA 2011 International Die Casting Design Competition Award. He is based in Pune. Over to Mr. Agarwal. Over to you, sir.
Good afternoon, everybody. Welcome to the training section on the casting defects in aluminum HPDC, high pressure die casting. Thank you, Mr. Soni, for giving me this opportunity to share some of the insights. So we will be going through the session today and we'll try to understand the various die casting defects. What are the engineering behind these defects and how we can address these defects. So what we'll talk about, one slide about the Texans, what all we are doing, and we'll continue our discussion with the what is the defect classification. We'll focus on the different type of defects, and we'll try to understand the root cause of these defects and what we can do to eliminate these root causes from an engineering perspective. Texans Engineering Services came into existence in 2017, and where we provide complete solutions to aluminum die casting, including gravity, low pressure, and high pressure die casting. We are basically working on the three verticals. One is the die casting process simulation. We provide the simulation services for the aluminum die casting, gravity, low pressure, high pressure on the Magma simulation software. We also work very closely with the foundries and the OEMs on the die casting process optimization, where we work on the defect reduction, rejection reduction, yield improvement, as well as other perspective on the process optimization like cycle time reduction on the shop floor. The third one is that we provide a complete solution and service for the dies, design of the die casting dies, including high pressure, gravity, and low pressure. We have a team of 12 designers working here in our Pune office. So where we work with the different customers to provide the design services. And the fourth one is of course the training part, where we provide the training on the die casting design, process, simulation, and the various other aspects of the aluminum die casting to the various foundries, tier 1 tool rooms, and various OEMs as well. Now let's continue our discussion. Those who have attended the last session must have seen this slide as well. So what is a defect? The defect is basically when the liquid material is processed and due to the various operating conditions, some defects are generated inside the casting, which renders the part unusable. Sometimes these defects are acceptable range, but a defect is a defect, it is always there. So in terms of the IPO, the input process output, we can say that the metal preparation, the liquid metal as an input, where we are processing the casting, we are generating the casting using the various ancillary equipment like the die and the machine, where the casting is produced, taking the shape of the die. And the secondary process, when the casting is produced, afterwards, whatever process we do on the aluminum casting, like cutting, shot blasting, painting, machining, all other are the secondary process. So what we'll be more interested in focusing is on the casting process or the defects generated during this casting process, which is like a black box. Once the die is loaded on the machine, it is look like a black box. So what is happening inside? So our focus will be there to understand what is happening there inside. NADCA identified 22 different type of defects, and basically based on the process understanding, we can define or we can classify these 22 defects as a cold defect and a hot defect. As we go along, we will understand why we are talking about this categorization with this perspective. You can see that most of the defects found on the shop floor you can see the defect images is the non-filling, cold shut, which are visible on the casting. You can see the different ways how it appear on the casting, sort of non-filling, cold joints or cold shut. Another defect is the peel off or the lamination, where the skin of the aluminum, solidified aluminum, comes out of the casting surface. It might happen during the secondary process as well as maybe during the initial casting formation itself. But mostly it happens during the secondary production process, like shot blasting or painting. The flow porosity, it is similar to non-filling, but sometimes it is inside the casting and visible on the surface also. So if you can see this defect on the cut section of a casting, it looks like a, let me just put the pointer. Yeah, if you see this defect, the middle photograph is look like a porosity, but it is not a porosity. It's like it is a due to the cold shut or the non-filling, but it is inside the aluminum or inside the casting. Similarly, you can see sort of like, the cold joint or the material has not joined properly on the left side image, you can see. Cold cracks, the crack formed at relatively low temperature, far away from the solidification range, where greater thermal contraction of the casting is prevented by the part or the die geometry. So you can see the crack line in the casting over here like this, or it looks like this, or it looks like this as well, the microscopic examination. It is, it is important to identify the defect properly before we go to the action plan or the detailed further analysis of the defect, what to do. So the analysis of the type of defect is very, very crucial and important to make sure the action what we are taking goes in the right direction. Blister is also sort of gas porosity. It is just same as the holes inside the casting. They are just near the surface and more visible. The trapped gas is under high pressure at the end of the filling, and when the casting is taken out of the die, it is able to push up the soft skin of the casting at ejection stage, creating blister. As the aluminum is still quite hot, and in the very hot regions of the die, the skin may remain the soft. And we're talking about this skin over here. The aluminum skin may be too soft, and as the pressure increases inside the casting during intensification as well, so the skin may pop up. It look like a bubble on the casting surface. Gas porosity, it is in the form of trapped bubbles, and it gives a distinctive look that typically looks like a series of smooth rounded holes. You can see a smooth shining surface, right? Even inside the hole, you will see a shining surface. That shining surface is mainly because of the gas, of the vapor, right? There are basically three types of gas porosity: steam, vapor, trapped gas, or burnt lubricants or inclusions. Edge porosity, it is similar to a blister which opens up at the main gate or at the overflow gate. You can see more clearly over here, just at the pointer there, right? Also, you can see at gate after the painting, you can see how it looks like. So it's a short tensile bar, the gate during filling, you can see how it looks like. And when the gate is cut off or the break, this porosity will be coming outside, right? Or after the polishing the casting surface or the gate. So we just have a few questions to understand and to elaborate. So what is common in these defects? Right? So one of the common point is that the metal freezes before the cavity is filled. So what we do to overcome? We increase the plunger speed, we increase the intensification pressure. What results do we achieve? We do achieve certain results, or the good results, I will say rather, good quality castings with these actions. But are these results consistent? If we are not acting on the root cause, the results will not be consistent. and the rejection pattern or the rejection graph will keep on moving up and down. What are the side effects? So these actions what we're talking about always has a side effect on the die as well as on the machine life. So let us try to understand the root cause. As some of you might have gone through, metal once leaves the holding furnace, it continuously loses the heat. It does not regain the heat. The temperature of the metal at the holding furnace is 660, assuming it is 660 for ADC 12. As it picks up in the ladle, it will lose the temperature. It pour in the short sleeve and phase 1 in the short sleeve, and the filling happens in the cavity and the solidification happens inside the die. So the metal leaves the holding furnace, it continuously loses the heat. It will not regain the heat. Overall, this is we're talking in general as an overall scenario to understand the basic phenomena. Also, the heat transfer by conduction is depend on the geometry of the medium, thickness, material of the medium, and the temperature difference. If we try to look in terms of the die casting process, aluminum is passing through the die on the both side, left and right. On the right side image is the mold surfaces, and there is a heat transfer Q1 and the Q2. And this rate of heat conduction will directly depend on the area, the temperature difference, and the thickness. Right? So that is a basic heat conduction equation, which is very, very useful to understand to dive deep into the die casting process. Also, considering this basic heat transfer equation, the NADCA defines the fill time requirement with the equation what is shown over here. If you see this equation, it is mostly consisting of temperatures, some constant factors, the casting thickness, and some percentage solid metal fraction, die temperature, liquid metal temperature, and so on. So it is basically the fill time requirement means is basically depending on the casting thickness and some temperature variables. So based on this casting thickness, we can see the fill time requirement. If you see, try to put this into the formula. So there are two calculations just to understand the impact of the different variables there, how it is impacting. So with a thickness of 3 millimeter, the fill time comes out to be 0.047 seconds based on these temperature conditions, and these are the constant factors and variables. If the die temperature is changed, rest everything is kept constant. Only one temperature variable is changed. The fill time requirement is changed. The fill time requirement is about 12% less than actually the original requirement. So it is less. As the fill time required is less, the increase in the short speed is required, means the plunger should move faster to be able to give the same results. That is just for indication. As we go along, we'll understand more in detail. So the fill time is the most critical parameter in the gating design. It depends only on the casting thickness and temperature conditions. Also, this is directly related with the various cold defects. We understand it again in detail as we go along. Due to the machine performance, flow length, and other temperature variables, normally we consider 75 to 80% of the calculated fill time while designing the die. Now, till now we have talked only about the fill time with respect to the casting thickness. The size of the casting or the weight of the casting did not come into picture. When we go to a particular casting and when we know the volume or the weight of the casting, so we have to convert this equation into the flow rate equation, right? And what is basically flow rate? Flow rate is the volume filled or the volume traveled or the volume supplied per unit of time. So we can say the Q1, the cavity volume divided by the cavity fill time. That is, we can say as the flow rate required. And when the cavity volume we talk about is the volume after the gate, and the fill time requirement is coming from the casting thickness. Now, how do we achieve this flow rate? So this flow rate can be achieved with the fast short velocity of the plunger into the plunger cross section area. that is VP into AP. We have to remember and make a note that the flow rate, the units must be same. When we equate these formulas, the units must be taken care. And the objective is to achieve the required flow rate in the machine with the proposed plunger diameter and the fast shot velocity. Similarly, when the metal is passing through the gate, the flow rate must be the same. So we can say that the Q3, the gate cross-section area into the gate velocity. Since Q2 and Q3 is same, so we can say VP into AP is equal to AG into VG. And knowing any three variables, we can calculate the fourth variable. Again, the objective here is to achieve the designed gate speed in the HPDC machine with the proposed plunger diameter and the fast shot velocity. Similarly, there is a fourth activity which is happening inside the black box or the die, the air venting. So before the aluminum or the liquid metal comes inside the cavity is filled with the air. That air must be taken out of the cavity. And how do we do? Mostly we provide the venting, the chill vent or the vacuum or the conventional venting. Conventional venting is something what we see on the top image, right? So how do we balance it out? So the flow rate of the air out of the cavity should be same as the flow rate inside. What is the metal is coming in? With the same flow rate, the air must go out. So with that flow rate, Q4, we can take out the vent area and the air speed, right? So by equating Q4 should be more than equal to Q2, we can calculate this air vent area and the air speed. Normally the air speed we assume in the range of 85 to 110 meter per second, which can go maximum up to 210 meter per second. Even if beyond this, the steel will start eroding, right? The objective here is to achieve the design venting area in the HPDC machine with the proposed plunger diameter and the fast shot velocity. Now, another important parameter, metal flow in the cavity. How do the metal flow inside the cavity? Is it a laminar flow or is it an atomized flow? As far as the high pressure die casting process is concerned, it is atomized flow. Because as we saw, the solidification time of the liquid metal is very, very fast. It is in milliseconds. It is not in seconds, it is in milliseconds. And we have to remember what is millisecond. 1 second have how many milliseconds? Right? The 1 second is equal to 1000 milliseconds, not 100 or 110 or 10 milliseconds, right? 1 second is equal to 1000 millisecond. And when we're talking about the fill time over here, we are talking about 40 millisecond, 30 millisecond, 50 millisecond. Means almost 20th or 40th time of the 1 second. It is a very, very short time to fill the cavity. So that's why if we are trying to fill the cavity with a laminar flow, the speed will be very, very less and the fill time will be much higher. The aluminum will solidify very, very fast. So to be able to fill the cavity with the atomized flow is only possibility to achieve the required fill time there and the quality of the casting in high pressure die casting. So this flow, what we're talking about, the laminar flow versus atomized flow, is mainly for the high pressure die casting. So what is atomized flow? Atomized flow is basically calculated by a given formula from the NADCA, where the variables are taken as the thickness of the gate, width of the gate, density of the molten metal, and the gate speed. And the atomized flow is look like the third one, right? The gate of the velocity is too slow, the medium speed and still too slow. But the third one is like atomized. It is like spraying the liquid metal inside the cavity. It is like spraying. So if you see the cut section of a casting along with the gate without intensification, it looks like exactly the same. It is like a porous material. Like or another example you can take like the foam. Like the foam of the chair or the bed, the foam. The foam is full of air inside, right? The structure of the foam looks like this. right? So this is the Nadka formula given to check for the atomization. For aluminum alloys, normally this J constant is 525 in metric units, not in inch units, metric units. So when we calculate this formula, the number which will come out should be more than equal to J, that is 525, to make sure we have atomized flow. Why atomized flow? We just talked about this. The cooling rate is very fast, and as I was talking about, it is not 40 seconds, it is 40 milliseconds, means 40 divided by 1000 seconds. And as the metal speed minimum desired for the high pressure die casting is 25 meter per second at the gate, it already comes to a speed of 90 kilometer per hour. Why we are converting this to kilometer per hour? Because it is easy for us to understand. We are easily able to correlate with the speed of our two-wheeler or four-wheeler when we are driving on the road. So we can see the scale in kilometer per hour. So this 25 meter per second goes to 90 kilometer per hour. And if you are feeling the casting at 50 meter per second at the gate, so you can imagine the speed will be 180 kilometer per hour, double of this straight away, right? So we have to be very, very careful. If we are trying to feed the liquid metal inside the cavity at a 50 meter per second or 180 kilometer per hour speed, you can imagine what is happening inside, right? So that's the reason atomization is a must to avoid or minimize the metal solidification during cavity filling. And once the cavity is filled with atomized flow, the melt is a mixture of liquid metal and air. Intensification cannot eliminate the porosity, it only reduces the pore size. If you see the slide over here, right, you see a pore size, right, very small, maybe 0.1, 0.2, or maybe 0.5. Or some of the pores may be bigger size as well, right? You can see the variation in the pore size. This is before intensification, right? So as we apply the intensification, the pore size reduces. The intensification lasts until the in-gate freezes. After that, pressure in the cavity quickly drops to vacuum and fills all shrinkage voids with gas. That is Boyle's law. Increasing intensification pressure may give some results, but may be not consistent if root cause of the gas is not eliminated. Now, here we are talking about two types of gases, right? One is that due to the atomization of the liquid metal, because it will always be porous, right? So there may be certain other amount of gases which we'll see in detail in the coming slide, right? So these gases will be entrapped inside the system and may lead to the bigger size of the porosities. One of the sources is the air entrapment in the phase 1 plunger speed, that is the slow short speed, runner and feeding system design, runner geometry, and the venting. The second source of gas is the steam vapor, which mostly coming from the die coat spray, as most of the foundries uses water-based die coat spray. The second is the water leakage. And the third source is the burned lubricants, mostly coming from the plunger tip oil. So critical slow short speed, Nadka defines a certain formula based on the fill ratio and the plunger tip diameter. The dP is the plunger tip diameter, Fi is the fill ratio, right? So this formula basically gives us a tentative indication on the critical slow short speed. The critical slow short speed, what we are trying to say, that the air should not be entrapped when the metal is moving, coming towards the gate. Because this air entrapped over here will not go anywhere. This will go and sit inside the casting only, right? So it is very, very crucial. The runner design itself plays a bigger role, right? We always have to have a reducing cross section towards the gate. The gate to runner ratio should be between 1 to 3. The minimum runner thickness also should be around 10 millimeter approximately for better intensification effect. The W by T ratio can be as small as 1. The maximum runner thickness should not be more than the biscuit thickness actually. Normally the biscuit thickness we keep 20 millimeter. So the runner thickness should not go beyond that. Runner to runner ratio should be between 1 to 1.1. What we're trying to say over here is, if you see the middle image, the cross-section area from the biscuit to the gate should always be reducing or increasing from gate towards the biscuit, right? So that is very, very crucial. So that helps to avoid or eliminate the air entrapment inside the runner. Steam vapor. Steam comes from the water on the cavity surface when the metal arrives. The gas is not present until the metal arrives. What we talked about, the air present inside the cavity, that is the air. That is slightly different than the gas what is being generated by the vapor. This gas is mostly trapped in the metal because there is a little chance to push the gas out of the vents. So it is mixed with the turbulent metal flow as soon as it is generated. And when water is converted into steam, we have to remember it expands to 2500 times its original volume. Even a small drop of water inside the cavity, the closed cavity, the volume of the gas generated is 2500 times. It's a huge amount of gas generation, right? And mostly by the die coat spray. The spray is for creating an insulation layer between the die surface and the metal. Uniform spray across the die cools down the die in some areas and leads to water retention in the cavity. Too much spray time also leads to water retention in the slide areas and deep cavities. In case of very cold die as well as very hot die, the water retention time in the cavity will be very high. It goes as long as 5 to 10 seconds. Many times we have a misinterpretation or the misconception. As the die is hot, temperature is 200 degree, the steam will evaporate or the steam will go out. But this does not happen actually because the retention time of the gas is very, very high. The die closed, the metal is poured in the sleeve, the metal come to the gate, second phase happens. You have sufficient time, but still the gas may be still there inside. So we must ensure the dry condition of the die before the next cycle starts. Water leakage, it may be there in the die. Many times we have experienced it in the shop floor. If you are having a particular gas porosity defect in a particular region, it always coming over there, then we must look for this type of defect. There may be some leakage of the water or maybe the hydraulic oil as well from the cylinders, right? It may be due to loose connection, cracking of the insert, dripping water from the overhead spray, leaking hydraulic cylinders, or the leaking plunger tip as well. So we should make sure that there is no water inside the cavity. The lubricants used on the die or on the plunger can generate gas when heated by the incoming metal. This gas is formed when the metal arrives, so it is not possible to force most of the gas out of the vents ahead of the metal flow. And all this lubricant give off some gas when heated to the temperature of the molten metal. The amount and type of gas will vary from lubricant to lubricant, but is also one of the very, very common defect found in the die casting. So what we should do? We should select the right plunger diameter, speed, fill time, right gate speed, gate area, venting area. And after doing all these, the thermal management becomes the most critical part, the next most critical part. So we should avoid the temperature drop during filling, maintain the right temperature, minimum delta, use of thermoregulation units, use of effective cooling methods. We will elaborate a little more on this as we go along the presentation for the hot defects. So right venting area, dry condition of the die, no water leakages, no excessive lubricants. So these are some of the actions we must take to make sure that we don't have this type of cold defects. Now, Are you able to grab the point why we are saying the categorization as the cold defect? Because the root cause behind this defect is mostly the same. The cooling down of the liquid aluminum due to the different reasons, right? Also, when we talk about the dry condition of the die, the air blow, usually the blow spray blow ratio should be in the range of 1:2:4. It's very crucial. Just to recap quickly, we have gone through the fill time understanding. What is the fill time, and depending on the casting thickness, the fill time is calculated. And when we talk about a specific casting, the design of the casting or the die, then we have to convert this fill time into the flow rate. And then we have the different flow rate, that is the Q1, Q2, Q3, Q4. And with the different flow rates, we can calculate the different variables based on the available inputs. Now, let's talk about the other type of defect, that is what we call as the hot defects. As we go along, we will understand why we are calling them as the hot defects. As the cast liquid metals occupy less space when they become solid, this empty space generated during the solidification process within a casting cavity is called the shrinkage porosity. It always occurs at the last point to solidify. So you can see the microscopic examination as well as the microstructure examination of this defect. So normally the solidification occurs from outside to inside. The liquid metal feeds the shrinkage, and when liquid metal stops feeding, remaining shrinkage leaves a cavity. The shrinkage normally occurs on the center line or the neutral thermal axis. So this neutral thermal axis is a full theory itself. So you can say, so like for example, in this casting, if you see the neutral thermal axis is coming over here. So this is the casting thickness from the core pin to this side, but the neutral thermal axis is coming closer to the core pin because the core pin temperature will be much higher, right? So the neutral thermal axis shifted towards the core pin. Sink marks are the visible depression on the casting surface. It is a form of shrinkage porosity. A sink forms when the shrinkage porosity is developed close to the casting surface, and as the casting cools, it pulls the thin skin on the casting surface in towards itself, forming a depression. Right? So this sort of depression is getting formed. Leakers. It is also a shrinkage porosity, but at a micro level and may not be visible. It is also called interdendrite or microporosity, developed during the solidification process. As you can see how the leak path is getting generated, getting connected. The areas machined away allow a leak path to exist between the machined sections, right? Another example over here, you can see the leak path. Hot tears. Hot tears appear due to tensile stress during solidification that occur at temperatures just above liquidus temperature, right? So the hot cracks occur in the last solidifying regions where thermal stresses are sufficiently increased. Warpage bending. The formation of the defect is related to the thermal contraction during cooling, causing local stress buildup. When extracted from the die, the high stress can cause plastic deformation, more pronounced in the parts ejected at high temperature with the drastic thickness changes. So this is just, it is more visible or more experienced in this type of parts. Soldering. Soldering is a compound formed by the combination of aluminum and the die steel. It becomes part of the die steel surface and keeps on building up, giving rough casting surface. It could be because of the metal speed or the temperature or both. It reduces the heat transfer rate from liquid aluminum to the die steel, causing internal shrinkage porosities as well as the leakage defect. And one more important point, when we do the die coat, the intention of the die coat, as we explained earlier, is to provide a bonding or a coating to protect the die steel surface. Right? If the coating is not done properly, the die steel surface will directly come into touch with the liquid aluminum and may still get stick and build up the soldering on the surface of the die. The left side image you see is the cut section of the casting, where you see the soldering impact on the casting. The right side image is of the die surface due to soldering. Erosion is the localized wear of the dies due to high velocity liquid metal flow. This is mainly observed near gates due to the high metal speed. Flash is the excess material inside the thin gap between the different die components or at the parting line. It could also be near the gate or opposite to the gate. It can be anywhere. Heat check phenomena is a thermal fatigue of the die steel due to alternate heating and cooling of the die surfaces. This leads to the undesirable surface finish and the die failure. The first graph what you are seeing is basically one cycle, right? So what is happening in one cycle? During metal injection, the die temperature goes up, and during the idle cycle, the die temperature goes down. Then it gain little bit because the die temperature goes down mostly on the surface, not inside the die up to depth, right? And then the next cycle starts again. So this cooling and heating of the die surface leads to the thermal fatigue. With the high temperature, the steel expands, the low temperature steel contracts. Gross cracking in dies, it's a thermal or mechanical overloading of a die which is into production, involving the unstable propagation of a brittle crack under tensile conditions. Presence of sharp corners, lower die temperature, low fracture toughness, or thermal fatigue cracks near cooling lines further add to gross cracking of dies. So what is the root cause? Die basically acts as a heat exchanger, right? Which absorbs the heat from the liquid metal, resulting in solidification of the liquid metal in the shape of the die cavity and pass it to the environment through conduction, convection, and radiation, where die acts as a heat exchanger. It receives the liquid metal heat and pass it on to the cooling, to the surrounding, to the spray, whatever is the surrounding, right? The total heat input to the die is defined as the latent heat of the metal and the sensible heat of the metal. And the total heat removal from the die is defined as from the cooling, from the spray, from the air, from whatever other means. The heat transfer by convection, that is mostly by cooling the third liquid, not directly, right? The heat transfer rate is defined by the heat transfer coefficient, area of the surface temperature, and the fluid temperature. Again, the delta, right? The delta temperature becomes the most critical factor. The higher the delta, the higher the rate of heat transfer. The lower the delta, the lower the rate of heat transfer. We can see it further in terms of the die functioning, as the cold fluid is passing through this channel, and on the top side is the cavity, and this is a hot die steel, right? In that this side, where you see the laser marker, the mouse, is the liquid aluminum, right? That's how the heat is getting transferred to the flowing liquid water through convection. The purpose of providing cooling in a die is to remove the liquid metal heat through the die during solidification, not to cool the die. The question is it possible and why? right? Because the heat input by the die is received only during or only as long as the casting is inside the die, or the liquid or the aluminum is inside the die. As soon as the casting is removed, there is no heat input to the steel. There is no heat input to the steel, but we continue to remove the heat. If we stop that heat removal after the casting is removed, will help a lot to minimize the delta further, right? Is it possible? The answer is yes, of course we can do it. We can implement the cyclic cooling or the interval cooling, where the cooling runs in the system only for a particular time of the cycle. Heat flows from high temperature to low temperature. The rate of heat transfer, again as we discussed, depend on the delta temperature. Now, another important question is, the heat input to the each region of a die is same. What is the answer? The heat input to the die at the different region is not same. You can see the result of three thermocouples at a different locations within a die, within the same die, right? As we have explained, as marked over here is a one cycle. One cycle is this much. So every cycle in the different regions of the die have a different peak and the low, right? Thermocouple 1, the minimum temperature is 205, maximum is 290. The thermocouple 2, the green one, the minimum is 165, the maximum is 285. The thermocouple 3, the magenta color, the minimum is 150, the maximum is 205. So these are the actual reading from one of the die running in production, where we put up the thermocouples and we took these readings. Why it is happening? The heat input to the die is not same everywhere. As you can see from this image, reference from Nadka, the heat input may not be same over here than this one, right? The heat input over here in this core pin, for example, is much higher as compared to the outside over here. The blue color you can see is the parting line. You have the two inserts, right? And the different regions of the insert. So the heat input is not same. So what we're trying to say, the hot and cold zone exist in the same die cavity, leading to various die casting defects, right? That's where we are trying to categorize these defects as cold defect and the hot defect. The cold defects are generated during the cavity filling, as the metal is getting freezed before the cavity is filled, and the hot defects are generated during metal solidification. That's the reason for providing or categorizing the defects in these two categories. The solution for each of these defects is opposite to each other. You remember I had mentioned in the beginning that defect identification is very crucial. The cold defect, you need to provide more heat. For hot defect, you need to remove more heat. If we are not able to identify the defect more clearly from the engineering perspective, then you may end up into the worsening of the defect situation, means the rejection may be increasing. Flash again is a defect which is caused by maybe by the mechanical design, the support below the insert, the sealing area, the blue matching, the centroid unbalanced load on the tie bar, centroid of the projected area, die area maybe too small, may on a big machine. Other reasons could be very high plunger speed, very high metal pressure, large die on a small surface, very high metal temperature, venting not enough. Machine parallelism are also some of the causes for the flash defect. Heat checks. This is basically showing the propagation of the heat check mechanism, how it is happening. And the heat check may lead even the removal of the metal or the cavitation. This is the image what you are seeing on a larger scale actually. So actually this size is maybe in microns. right? The temperature delta during the production run should be minimum. Means what? Minimum spray time and quantity, minimum pressure of air and die coat, strong internal cooling. We should run the die as much as possible continuously, no major or minor crack breakdowns, or as well as the larger batch sizes. Die preheating, external by LPG gas burners or internal by oil heating or by use of thermoregulation. What happened with the external gas heating? LPG flame. So this is the standard image of the gas flame and the temperature associated with the color of the flame. Okay. The green color itself is 1000 degree, or the cyan color also is about 830 degree. Blue color is 602 degrees Celsius, right? What is the tempering temperature when we do the heat treatment of the die steel? The tempering temperature is about 550 plus minus depending on the steel grade and the quality of the steel, but it is into this range. Some people use 555, some people use 545, right? If my flame is touching my die surface above this temperature, above blue color, right? The hardness will be lost. And once you lose the hardness, tensile strength will go away. It will again further lead to the early failure. Even within few hundred shots, we have practically seen so many dies failing or the heat check starting within few hundred shots. And when we went to the analysis, this is one of the major root cause. Distortion crack in the dies, stress is developed during the die manufacturing left unattended, stress relieving not done regularly, thin steel sections, robust die design is not there, die preheating, increase the fracture toughness of die steel, but external heating is not good because it only heat up the surface, increases the risk of failure as internally steel is still cold. So what should we do? We should provide each zone of the die must be analyzed for the heat input and heat output. Provide internal cooling accordingly to remove the maximum heat during solidification. Partial local squeeze to compensate for the shrinkage volume. Jet cooling, 3D profile cooling, that is additive manufacturing. We may need to add heat, remove heat at the same time in the die. That is where the use of thermoregulation comes into picture, as well as the customized spray heads. Even though, as we discussed, the spray heads are not designed or useful or to be used to cool down the die, but due to the limitations, the design or the product design, we may still have to do that. So proper structural design of the die to suit the machine, proper control of the process parameters, selection of the steel grade, heat treatment parameters, die manufacturing process, minimum or zero EDM, proper preheating of the die, large batch sizes. Further actions for this hot type of defects, one of them is the partial squeeze or the local squeeze pin to compensate for the shrinkage volume, where intensification is not able to reach or is not enough to feed the shrinkage volume. Jet cooling, you can see the example in front. It is internal cooling which is mostly used in core pins or loose inserts to have focused cooling impact in the cavity where heat needs to be removed at a very fast rate. Additive manufacturing is a profile 3D cooling, internal cooling, right? This is the part of the one of the projects we did at Texans, where this is the actual core pin you see on the screen. So we designed, manufactured, put in production process, and the effects are amazing. Thermoregulation is it can be either oil-based or water-based heat exchanger unit, which provides cooling as well as heating effect to the die. So basically, as we know, the heat flows from the high temperature to the low temperature. It removes the heat where the temperature is higher than the required, and it adds the heat where the temperature is lower than required. So it both ways, it acts very intelligently. Customized spray heads. These are the spray heads, standard spray head if you see on the left side, and rest all are the customized spray head, examples of the customized spray head. We had used many of them in our shop floor journey, and it is very, very useful. The important message over here is that the spray heads are no longer a part of the HPDC machine, but the spray head is a part of the die change. We take hours and hours to change the die, but we don't bother to look at the spray head. So the important is to understand the criticality of the spray head and make it as a part of the die change. As we change die on the machine, we change the spray head. Again, is my standard practice as well as the phenomena. Integration of the product design, tool maker, and the die caster as one team is the key to success in die casting. If any one of the parameter is missing, it may lead to the failure, or maybe incomplete success, or maybe more struggle, more time lost. So with this, we come to an end of our session today. I hope I was able to give you some tips and the engineering background behind the root causes of these defects, and should be able to make use of this learning. My special thanks to NCTS, the Institute of Indian Foundrymen, especially Mr. Soni.
Thank you for the detailed information on die casting defects, giving explanation on root cause analysis and then remedies actions to be taken, the difference between hot and cold defects.
Yes.
Theory behind, coupled with explanatory equations and photographs, made it really easy to understand. Thank you.
Thank you so much.
Thank you, sir.
Thank you so much. Thank you.